Hello students, in our last class we discussed about PN junction diode, right? In PN junction diode we discussed about barrier potential, we discussed about depletion layer, we discussed about drift current, we discussed about diffusion current, and finally we said in steady state there is no current in it. Okay, PN junction diode is ready but there is no current in it. So it's very similar to conductor. In conductor also there will be no current unless we connect it with a battery, or rather we apply potential difference across it. Okay, same thing is here now. A semiconductors we made ready in the form of PN junction diode. And now when PN junction diode we are going to connect with the battery, then we will see current in that one. There are two ways in which we connect the battery in this one. One is called forward bias and another one is called reverse bias. In conductor that choice is not there. However you connect the battery you will be getting the current. But it's not in semiconductor. As we said that it also controls the direction of current, right? So there are two ways in which we connect the battery across PN junction diode. What is that? One is forward bias. Okay. So forward bias. What is forward bias? When P-type semiconductor, we are connecting with the positive terminal of the battery, and N-type we are connecting with the negative terminal of the battery. Then it's called forward bias. Okay, but before that, how PN junction is actually denoted, or what is the symbol for that? That also we should know. Okay, so PN junction diode we represent like this. This is P, this is N. Okay, this is a symbol, a triangle and a straight line. This is called P, this is called N. This is PN junction diode. Okay, but this way, if suppose, okay, in this way also if I show you forward bias, then it's like this. Okay, this is called forward bias. But with this one we will not be able to understand. So we have to go back to the original one, how to make PN junction diode. That way we can understand it in a better way. Okay, so here is P-type semiconductor, right? This is P. So what is this? There are holes. Okay, I am showing you here only because in the remaining part I will be making the depletion layer, right? So these are holes here and these are electrons. Okay, and this side is N. Okay, and this one here there are electrons and some holes as minority charge carriers, and this is depletion layer, right? Yes, we have studied before in the last class. In depletion layer, what happens? We all know that electrons from here, which are in conduction band, having highest energy, they will move on to the P side and occupy the holes, occupy the vacancy. Okay, so since these electron goes to this side, okay, this here becomes a negative because this P in general was what? Neutral. N in general was what? Neutral. So from here, when from electron from N to P they have gone, so N has lost the electron, it becomes positive, right? And this becomes negative. So here there are electrons, right? Too many I made. Okay, here are holes. So this becomes positive here, this becomes negative. So electric field is like this. This is what we studied in PN junction diode. Okay, this is depletion layer and there is some barrier potential between these two, right? This we have done. Now we are making it forward bias. So we are connecting it with a battery. Let's have a switch over here and then there is a battery here. Right? Now at the moment what is there? This I have not switched on. It's not switched on. So now there is no current in this one. No current at all. Any electrons are able to move to this side? No, because this electric field is not allowing them. This electric field or this barrier potential is not allowing this free electrons to jump to this one. Right? Correct? Okay. Now when we apply this potential, now what it is? This is positive, this is negative. So what is the direction of this electric field? Its electric field is like this. Okay, that means this one. This is outside electric field. Our question is it in the same direction or opposite direction? Opposite direction. So this electric field is going to apply force on these electrons. Okay, this electric field is going to apply force on this. So till this outside electric field is smaller than this inside electric field, nothing can be done. Okay, nothing can be done. But once this electric field becomes greater than this, that means there will be more force on these electrons. So what will these electrons do? They will start jumping. Okay, this will start jumping. Not jumping means they are able to cross this depletion layer. Okay, they will be able to cross this depletion layer and they will start moving this side. These electrons will keep on moving this side, like this, like this, like this. Okay, so motion of electron started. When motion of electron is starting, what will happen on this side? This p side, what is happening? As electron is moving this side, here, whatever covalent bonds are there, those covalent bonds are breaking because of this electric field. Here also this electric field is going to apply force, right? So here also covalent bonds are going to break. As once the covalent bond is breaking, electron moves in this way towards the positive side. Once we are closing it, okay, then only it's happening. Okay, see, listen again. This electric field is applying force on these electrons. Electrons are able to move this side, right? So then they are going to move this side. What they are going to do? Their vacancies are there. They are going to occupy the vacancies. Okay, one. Second thing, what is happening? On this side also this electric field have its effect. What effect? This electric field is going to break the covalent bonds here. Right. So when it is going to break the covalent bonds, where will those electrons go? Those electrons move this side, like this. Okay. Those electrons, from here electrons have gone this side. So there is shortage of electrons. No, they have already moved this side. So how we have to complete it? Because current means is, what we say? Normally in a conductor, what we say? Whenever you are connecting a conductor with the battery, okay, the charge which is flowing out of this one, same charge has to come this side here. Same charge, no? Correct? So, if suppose from here, these electrons which are coming from here, this side, same electrons will go this side. Okay? So, here again, there is incoming electrons are there. And those electrons again will go this side, occupy the vacancy. Same number of electrons here will come out because of the breaking of covalent bonds. And then again those electrons, like this, we will be getting the current. Okay, how will be the current? Current will be in this direction because motion of electron is like this. So this is how we are going to get the current. Okay, so first was what? When it was not connected, we were not getting any current. As we connected it, we were able to apply certain force. So maybe some electrons were able to go initially. When this potential becomes more than barrier potential or outside electric field is more than this electric field, then more charge carriers, more electrons are able to cross. As we are going to increase it, more and more electrons will come. But at one stage, it will become saturated. Right or not? One stage, it has to become saturated. When all the electrons, whichever electrons are coming over here, all the electrons start moving, then it will be saturation. Correct or not? Right? So, this is how we are going to get forward biasing current. Okay. Right. So, when all the electrons which are reaching here are coming over here, the supply becomes like a conductor. That's what we want, right? It has to replace the conductor anyhow. Then I will say that we are getting the saturation current. Saturation doesn't mean that it is becoming constant. It becomes means maximum. Okay. Is that clear? So this is forward biasing. How is the graph? Characteristic graph, that's important. Okay. So characteristic graph, IV graph. Okay. This is I and this is V. Which V? Battery. This one. Okay. So when it's zero, current is also zero. We all know that. Okay. Current is also 0 when V is 0. Okay, but once it reaches barrier potential, after that it increases very sharply. Okay, so maybe here we can say barrier potential. Okay, so up to this point, very less. Okay, after this, not this way. Okay, let's see. This way, then it goes like this. Okay, this here we can call as cutoff voltage or knee voltage or cutoff voltage. And we know their values also. What? For silicon it's 0.7 and for germanium it's 0.3 volt. Okay, this V dash, let's say V dash for germanium 0.3 V and V dash for silicon is 0.7. Okay, and what current we are getting? What is the magnitude of this current in milliampere? This current that we are getting will be in milliampere. Remember that. Forward bias current is obtained in milliampere. Okay, this is forward bias. Simple, no problem, right? You write it in your own word because in board you have to write it. Board question will be asked, what is forward bias? So entire thing what I explained you have to write and then you have to make this characteristic graph. Okay, right. Now what? What is the other way we can connect battery? It's called reverse bias. What reverse bias is? Reverse bias. Now reverse bias we are going to connect P type semiconductor with negative terminal of the battery and N type semiconductor with positive end of the battery. Okay, and I have told you how to make PN junction diode already. Okay, so that diagram also I will be making. This is your PN junction diode. How we are connecting it? Connecting it like this. Okay, but you can understand it from that. So we have to make it usual one. Okay, so here is your P type. This is N type. Okay, so P type means there are holes and these are electrons. Here there are electrons, minority charge carrier is holes, and this is your depletion layer. And in this side, what is there? Here there are electrons and there are holes. And this is positive, this is negative, right? And there is electric field. Depletion layer electric field is on the left, right? Okay, let's connect it with the battery. Here is switch. We connected it like this. Okay, so this is positive, this is negative. Now, how is its electric field? Outside electric field. Outside electric field is like this. That means in this way. So outside electric field and this inside electric field both are in same direction. What they'll do? There are no chance that these electrons can move to this side. No chance. These minority charge carriers may move. Some drift current will be getting, but more than that, nothing. Diffusion, not at all possible. No diffusion. Okay, in the previous case in forward bias, our current was in the same direction as that of diffusion current. Okay, clear? Fine. Now what is going to happen? Now, because of this one, now these electrons will go further outside. Because this depletion layer or rather the barrier potential, because of the electric field has become even more stronger, right? So starts increasing. What will happen is there is a force on these electrons. In which direction? This direction. They'll all go in this way, and these will go in this direction. Okay. So depletion layers width will increase. Okay, it's going to increase a lot. Right? What will happen? Say that it is increased, then increase it a little bit. Right? So maybe we can say up to this now is the depletion layer. Okay, and these in between, these just remove it. Okay, so depletion layer has its thickness has increased. Right, so what will happen because of that? That also I am explaining you. This is not depletion layer. Okay, this is increased, more potential. Right, what has happened now? As I said that on these electrons there is a force in this direction. Correct, and on these holes also there is a force in this direction. So electrons, these electrons, minorly charged carriers can still move. Very small drift current we will be having, but other than that, there is nothing much of a current in this one. Right? No current is possible. Now what is going to happen? This electric field is very strong. So now because of this electric field, these covalent bonds which are in depletion layer, that's going to break. That is going to break. And once this is going to break, pairs will be created, holes as well as electrons. Okay, within this. Now you are seeing these electrons over here. This is basically are making covalent bonds here, right? So this has to break. This is a covalent bond here. Okay. So because of this electric field, you can see that I am going to increase it continuously. Okay, unless I get current, because I want current, so I keep on increasing. So at such a stage, when this electric field that you have applied from outside, this is able to break these covalent bonds from here, then what will happen? Positive will go towards P side, negative will go towards this side. And since it is through this electric field, it is broken, covalent bond is broken, and after that it has to still cross this much distance, right? What this electric field will do? It will give it certain velocity, that means kinetic energy will be given to electrons. So those electrons will go and they will move this way. Okay, those electrons will come down to this side and connect with these holes. So once they are connecting with these holes, covalent bond is made again. Okay, and from here this is breaking and those electrons are coming and here again making covalent bonds. So this cycle continues after that. Okay, you keep increasing this one. Okay, current also will increase. Right, this is how we get current in reverse bias. Okay, but basically breaking of these covalent bonds happen in two ways. What I explained you right now is called Zener breakdown. Okay, what it is called? Zener breakdown. That means you increase the applied potential to such a value that these covalent bonds start breaking. And once they start breaking, what will happen? We get lot of electrons, because it's not that one bond only will break. All of a sudden, many bonds will break. Okay, so many bonds are going to break. That means you will be getting ample charge carriers, and because of that, we will be getting current. Okay, that's called Zener breakdown. Right. There is another one which is called avalanche. Avalanche breakdown. Now, what that is? Okay. Now, avalanche breakdown is, we all know that because of this electric field, these electrons and minorly charged carriers will pass through this. Okay. It passes because electron always move opposite to the direction of electric field. So these electrons, minorly charged carriers, can move. So when they are moving from here, they are getting kinetic energy, right? So with that kinetic energy, if they are going to collide with any of the electron here, so because of the collision also covalent bonds break, and because of that breaking also we will be getting pair, hole and electron again will start moving in this direction. So because of that also we get current, and that's called avalanche breakdown. Okay. Zener breakdown means is these covalent bonds are breaking because of the external electric field. Avalanche breakdown is because of the motion of these minority charge carriers which are moving through this and breaking covalent bonds, and they are getting the current. Avalanche breakdown current will be a lot lesser than Zener. Okay. Zener is kind of, you can say, maximum current that we are going to get. Okay. So this is how reverse bias work. Reverse bias current is in opposite direction because it's in the direction of drift current, whereas forward bias is in the direction of diffusion current. Okay, is that clear? So this is reverse bias, correct? Okay, so how is its IV characteristic? So IV characteristic is like this. This is I and this is V. Okay, forward bias current we got in this direction. Reverse bias will be getting opposite direction because it's in the direction of drift current. So how it is? It's like this, almost straight. Forward bias, if you see, you just go back and see forward bias. Forward bias is like this, but this is almost straight. Okay, it's almost straight. You can make it almost straight over here, like this. Okay, this is reverse bias current. And how much is its value? This is in microampere. Okay, this is not, doesn't have the magnitude of the forward bias current. It's a lot lesser. Okay, this is in microampere. Whereas forward bias was in milliampere. Remember that, because in that one majority charge carriers were responsible. Majority charge carriers are huge in numbers. Here, who is there responsible? The charges which are there in depletion layer and minority charge carriers. They are responsible for this current. So its magnitude is a lot lesser as compared to forward bias current. Okay. Now, reverse bias we studied, forward bias we studied. Now, reverse bias resistance is considered to be very, very high. It's infinite resistance. Okay. Resistance of reverse bias. Ideally, it should be infinite. Okay. And forward bias resistance is very less. Okay. Resistance of forward bias is very less. Ideally, it should be 0. Ideally 0. Okay, clear? So whenever we are connecting a PN junction in forward bias, current can easily pass through that. But if you are connecting it in reverse bias, current will not pass through that. Okay, that's how we control the direction of current in the circuit. Okay, whenever we don't want, we connect PN junction in reverse bias. The current will not. Okay, so this is how we are connecting a battery and making forward bias and reverse bias in PN junction. Okay, done? Questions on this one we'll do in the next class. Okay, all the questions we'll take, PN junction diodes, all the questions. Right. Now what? Applications. Applications of PN junction diode. What are the applications? Let's see. So first application we'll see is rectifier. Okay, rectifier. What is rectifier? A rectifier is a device which converts AC into DC. Okay, a device that converts AC into DC. Okay, now two types of rectifiers are there: half wave rectifier and full wave rectifier. Well, first let's see half wave rectifier. half wave rectifier. Okay, what it is? First thing is we have to convert AC into DC. That means input is AC. Okay, and output should be DC. DC means what? In which fluctuation in the value of current should be along one side, not on the other side. It should not be positive and negative. Either should be positive or it should be negative, not both. Then we will call it as DC, right? Okay, so half wave rectifier it is. So how we are making half wave rectifier? See, we are using a device which we already studied. Okay, let me make it, then we will discuss. Okay, the device is like this. What is this called? Remember, this is transformer. Okay, this is transformer. Okay, this is transformer. Now here is PN junction diode, right? And here we will make output here. This is called load resistance. This is output. From here we will be getting. Okay, this is PN junction. And here we are giving the input. How is the input? Like this. AC input. Okay, so let's first talk about the positive half cycle. This is positive half cycle. Okay, it's positive half cycle. So when we are talking about positive half cycle, we know that this will be positive, so is this. This is negative, so is negative and positive means basically what? Higher potential, lower potential. That is the meaning. Okay. So this is positive. Now positive is connected with P. So what will happen? It will allow the current to pass through that. Okay. It will allow the current to pass through this. So we are going to get the current in this way and we will collect it from here. Okay. There is no problem. Fine. This is negative. So negative is here. Pn. It will allow current to pass through that. Right. Then negative half cycle. So when negative half cycle is coming like this, so what will happen? This will become negative. So this will become negative and this will become positive. So here also negative and this is positive. So what will happen? If this is negative, this will become reverse bias. Negative half cycle, this will become reverse bias. Now current, will it allow current to pass through? No. It will block it. So are we going to get current over here? No. We are not going to get current over here. So because of this reason, we are going to get only half of the wave. Okay, not full wave. So we call this as half wave rectifier. Okay, so how is the output? Output is like this. Okay, because only half wave got rectified. Okay, so if we make a full diagram in which we show the input as well as output. Okay, so how it will be? It will be like this. This is input. Okay, this is input. Okay, so and let's have the output here. Okay, output is like this. This is output. Okay, and that is input. And this part is missing. So because of this, what happens? Efficiency decreases. This much energy is gone. Which energy? This much. So you say that why not make it as a full wave rectifier? Okay. We can make full wave rectifier also. Right. So let's see what it is. Full wave rectifier. This full wave rectifier. Now full wave rectifier will be using two PN junction diodes. Okay. Exactly same diagram. Transformer. Okay. Right. Here we are making one PN junction diode, and here also we are making one PN junction diode. Okay, then what? Here is load. Okay, then you connect it from the middle. This is load. Okay, so output will be getting from here. Okay, here is the supply. So we all know what is going to happen, right? See, a positive half cycle for this. Or this is positive, this is positive. This is negative. So this is PN junction, this is forward bias. So we are going to get load from here. Correct? No problem here. But then when reverse bias is there, so when reverse bias, not reverse bias, sorry, the negative half cycle is there. When the negative half cycle is there, then what happens? This becomes negative and this becomes positive. So is this negative, positive. So when this is becoming positive, this becomes reverse bias and this becomes forward bias. Positive is connected with positive. No, this is PN junction. So then this conducts. So then when this negative half cycle is there, this is conducting the current and we are getting it. So what now? We are able to get full wave and rectified. How it is, just see. Okay, this is input. Okay, this is input. And then how is the output? Output is like this. Current is in same direction only. We are getting current in same direction here. Current direction is not changing. Whether it was like this or it is like this, current is coming in same direction. Rectified. Now there is another work that we have to still make it as a constant value DC. That we will be doing with the help of inductor and capacitor. But in this PN junction diode, it is able to make it unidirectional. Okay, so this is converter. Okay, conversion of AC into DC. Okay, note this one. Right, students. Now there are certain special type of applications. What are those? Light emitting diode, photodiode, and solar cell. Okay, those three also we have to study. Okay, so let's see. First one we are going to see is light emitting diode, LED. We all know about that, right? Light emitting diode, LED. Now almost all the lights in our home are through LEDs only. Other than that, our TV screen, LED, monitor screen, LED, mobile, LED. Okay, so we are actually using LED everywhere. So LED is what? Actually PN junction diode only. What is LED? A PN junction diode only. So its working we are going to see, and its diagram we are going to see, and its characteristic also we will see. Okay, So light emitting diode. Okay. So what happens in light emitting diode? It is going to emit light. Okay. It's going to emit what? Light. So how we are going to make it? PN junction diode it is. Right. How it is connected? Say connected forward bias. PN junction diode we are connecting in forward bias. So I can connect like this now. Because we know that what is the working, right? Okay, we'll make one switch, right? So this is connected forward bias. Before connecting with it, we all know that the no current in the PN junction diode, diffusion current, drift current are exactly equal. Steady state is there. We are not getting any current, right? No flow of electron from here to there is happening. We connected it with the forward bias. Now what happens? Electrons start moving from N side to P side. Okay, because of the external electric field. And these electrons, which are high energy electrons in conduction band in N semiconductor, goes to valence band in P type semiconductor because their holes are in valence band only. They go to that, and while they are going it, are they going to release energy? It's obvious. When you jump from conduction band to valence band, obviously you will release energy. Correct or not? So energy is released. So energy is released means photons is released. They are releasing photons. Okay. They are releasing photons. And if it is of the wavelength that falls into visible spectrum, we are able to see it. In fact, LEDs are there which are producing the visible spectrum only. Okay, so wavelength is from somewhere around 3800 to 7600 angstrom. Right? So this is LED function. Very simple, right? When electron jumps from N side to P side with the help of the external battery, forward bias, because it was not happening earlier. So when electron from conduction band goes to the valence band of P side, it releases energy, photon, and that is in the visible spectrum. We are calling it as LED. Now for different colors, different wavelength is required, we all know, right? So we can get LEDs of different colors, maybe red, maybe violet, maybe yellow, green, blue, all are possible, depending on how much is the energy gap. Correct? How much is the energy gap between the conduction band electron and the valence band. Right? Is that clear? So lambda will be what? We all know. Lambda will be Hc by the energy. Right or not? Or energy gap, you can say. Eg. Correct? Clear? So this will be there. In angstrom, if you want, we all know that for that also 12,400 we have formula. Correct? Lambda in angstrom, 12,400 by volt. Delta V you say, not volt. Say that delta V. Okay, so this will give us wavelength in angstrom, right? So these are all we know. We have studied that before. Correct? So that's light emitting diode. I hope you understood the working. Okay, note this first, then you will see its characteristic. Let's see its characteristics, students, then. Characteristics means what? Again, IV graph. That is only called characteristic. So IV graph will be similar to forward bias because it's a forward bias only. Right? It will be forward bias or something like this that we have seen before, right? Okay, but in this one, we all know that it's a LED. We have seen LEDs of red color also. We have seen LEDs of violet color also, green color also, yellow color also. Okay, so how is that? It all depends on this delta V. What is this delta V? potential difference between the energy gap. Energy gap is what? Conduction band and valence band. Energy is there, right? That we are measuring in terms of delta V. So it depends on that, right? If you want red color means maximum wavelength. So that means this delta V will be less. If you want violet, that means minimum wavelength. That means this delta V should be on the higher side. Okay, correct. So this is how we are getting LED. This is the working principle of LED. Very simple, right? Same way now, let's see photodiode. Photodiode. You have to remember all this, okay? Photodiode. Now photodiode is highly doped. Photodiode is highly doped. Doping in general will be high in all, but this is very highly doped. And this is connected in reverse bias. Okay? Connected in reverse bias. That means there is no current. Reverse bias means no current, right? The reverse bias, now what is going to happen if you are connecting in reverse bias? Let's see, I am making this way only. PN junction diode. This is how it's connected in reverse bias. There is no current, right? So what do you want in this one? In this one, we want light to fall on this. Where? On depletion layer. When you have higher doping, depletion layer also will be more thick. Okay, more thicker. So these photons are falling on the depletion layer. What is going to happen then? Covalent bonds are going to break. And covalent bonds are going to break means electrons will go towards N side and holes will go towards P side. And because of that, what will happen? We will get the current. Small current we will be getting. Right? But this is having highly doping. So current may be more than what we saw in the normal case of reverse bias. Okay, so we will be getting current. This is how we are getting the conductivity in this reverse bias circuit. Okay, this is photodiode. Where we use it? In all the sensors. All the sensors works on this. Okay, sensing devices. Sensing devices, all the sensors. Like when you are going somewhere, maybe auto door, automatic door is there. When you stand in front of that, it opens automatically. How does it know? What you have done? You have just stopped the sunlight which was coming onto this. So what happened? Circuit is broken. There is no current in that. When no current is there, door opens. Once you move out from there, again sunlight is coming. Again circuit is complete. Current is there and okay. This is how photodiode works. And how is its IV characteristic? In this one, this is drift current. Reverse bias means drift current, forward bias means diffusion current. The direction will be opposite, right? So IV characteristic, how it will be? This is I, this is P. Okay. So how it is? This in this one, because it depends on these photons. So we get saturation current very easily. Okay. So it's like this. If we increase the energy of photon, like this. Okay. I1, this is I2. Right. If you increase the intensity of photons, more current. Intensity of photons, you know that. Intensity of falling energy means more number of photons are falling. More number of photons are falling means more electrons will be released. More electrons will be more, we are getting more current. Okay. So if intensity is increased, we will be getting more current also. Clear? This is photodiodes. Now the question is, what is the need of this junction diode to be used as in the case of LED Normally also we have bulbs, right? In LED, why we are using PN junction diode? Reason is, first thing is size is very small. We have discussed it. Okay. And functioning is immediate. There is no lag. Here also, if you stand in front of the door, opens automatically very fast. No lagging. Okay, no lagging. Very long life. Okay, they are not heavy, small devices. Okay, long life. Okay, very less loss of energy. Okay, normally in a bulb you see you touch it after switching it on for some time, you will find that it's very hot. LEDs are comparatively less energy consuming devices. Okay, that's why they save a lot of power. Lot of power they save, right? So there are many advantages. That's why we prefer semiconductors now, PN junction diodes over the normal devices, right? So this is photodiode. Note it fast. Two more applications are there. So we will see both. I'd like to finish this theory part of this one. And then in the next class, we should see logic gates. Okay. Now that's photodiode. Then, now then what? Solar cell. Solar cell also we should see. In solar cell, we have very highly doped PN junction diode, but it is neither forward bias nor reverse bias. Okay, no battery is connected. Okay, highly doped. Okay, now I have to make PN junction diode to show you in this one what is happening. Okay, just to see them. Okay. Wait, this is depletion layer. This is P, this is N. Okay, so here are your electrons. Highly doped means depletion layer also will show the same thing, right? Okay, these are holes here. Then we have in general our electrons and holes. Okay. It's like this, and it's okay. First we'll have open circuit. Right, now what's happening? It's a solar cell. And that means we are making sunlight to fall on it. The sunlight is falling. We know that what will happen because of that, right? Where we are making it fall? On entire thing it is falling actually. But maximum effect will be seen where? The depletion layer. The depletion layer, these are incident and these covalent bonds are breaking. So when covalent bonds are breaking, what happens? Your electrons will come to this side. High energy electrons, yes or no? Yeah. So all these electrons will come on this side, here. Okay. So this side over here, electrons. This becomes negative. And this side what? Holes. What will come this side? Holes will come this side. So this side holes are coming. So this like this. And this becomes positive. Potential difference is created. Right? Potential difference is created. Maybe this is the maximum potential. Maximum potential. Whatever is the maximum potential, that is we have created. It's open circuit. We have not allowed current to pass through that. Correct. And if you want, we can keep a resistance over here. resistance we can keep. When we are going to switch it on, we will be getting current. Okay, so current will be like this. This is the direction in which current will be coming. Okay. The direction drift current or diffuse current? Which direction it is? Diffused. Drift. This is the direction of drift current because it's from depletion layer. Electrons are going in this way. Whereas in diffusion, electron go from N to P. Right, here is coming from direction P to N. So it's direction of drift current. So we get like this. This is the working of solar cell. Clear? A characteristic. Okay, so understand characteristic. First of all, we are going to keep it in open circuit. So when open circuit, that means this is not connected. So what we got here? Maximum potential difference. So let's say maximum potential difference positive. Yeah, positive potential difference. So V open circuit. This is maximum. Okay. Now what we are going to do? We are going to short circuit it. Short circuited means this resistance also you will not have. So let me make it like this first. You connect it like this. Now what will happen? What's going to happen? Current will flow. Current will flow means electron will flow, right? So current will flow, positive to negative means current is like this. Which current? High current, very high current, right? Because there is no resistance. Very high, delta V by 0. So very high current. Okay. What's going to happen? These electrons will move here. This side, electrons will go this side now. Right? So covalent bonds will be forming here. Photons are falling here also, right? Yes, they are falling on all. So whatever number of electrons are coming from here to this side, covalent bonds are made, and then because of this light, broken and goes. So what will be happening? Saturation will come. Electrons are coming, same number of electrons are going, same electrons are coming, same number of electrons are going. Correct? So one stage will be here, there is no formation of electron, no electrons will be here because whatever electrons are coming directly. So potential difference between these two ends will become 0. There is a direct flow. Continuous flow is happening. We get maximum current. Right? But here and here there will be no potential left. This is called short circuit current. Maximum current, short circuit current. So here maybe I short circuit. Okay, let's join this. It's like this. So here potential is 0 but current is max. This is called short circuit current. This is maximum potential difference when it is open circuit. As we are going to connect it, this potential difference is going to decrease. And when we are going to short circuit it becomes 0. Okay. This is VI characteristic of solar cell. Okay, note it. Right? That's solar cell. Now we'll see Zener diode. Zener diode. What is Zener diode? A special device which is used to control or regulate the voltage. Okay. It is used to regulate the voltage or supply. Okay, it maintains the constant potential difference across the appliance. If suppose one appliance is connected along with the Zener diode, it will make sure that it is getting constant potential difference. Okay, if the supply is having variation also, it will not affect the appliance, right? So how it is connected? It is again very highly doped, very highly doped. Okay, and there is a different symbol for this one. This is for Zener diode. Okay, for normal PN junction diode, we are having a straight line. Now it's a different way. Okay, this is Zener diode. It's connected in reverse bias. Okay, PN junction in reverse bias, highly doped. It's called Zener diode. Okay, how it's going to control, how it's going to regulate, we'll see that. Okay, first note it. Done? Okay, see. So, what we are going to do, we are going to have a resistance here. Okay, this is the supply, positive, negative, and here is our PN junction diode, and it is connected in reverse bias, we are saying. Okay, so we'll shift it a little, right? So it's in this way. And then it's obviously it has to be connected with the appliance, and appliance has to be in parallel to that. Okay, so here is appliance of yours. So it's a Zener diode. Zener diode means, remember that what I told you, breakdown, Zener breakdown. Okay, so Zener breakdown means is when Zener breakdown happens, then only the current will start flowing through that. Okay, so that Zener breakdown, let's say it's Vz, it's constant. At what it is going to happen, it's constant for this device. It's not going to change. And accordingly, we can design it that how much should be a Zener breakdown. Okay, so that Zener breakdown potential is over here. Okay, this is a supply. This is some external resistance we have. So what happens if suppose that this potential, when it is less than Zener breakdown, no current passes through this. No current passes through that. Okay, and what is the potential over here? It maintains that potential. There is no problem. So current will mainly be going like this. Because this is in reverse bias, it will not allow any current to pass through that. Very simple. All the current passes through the appliance. But when this potential becomes greater, okay, becomes greater. So what will happen then? On this one, when there is potential equal to Zener breakdown or greater than that, then what happens? Breakdown happens in this, and this allows current to pass through that. So the current which is coming from here, it will split. It will split in the two. So the current which is going into this one will have same potential as that of this, because it's connected in parallel. So whatever is Vz, same Vz will be getting here. It will not be getting more. Okay, because this Vz is not going to change. The breakdown of this one, when this breakdown is going to happen, this potential difference is going to be same only across the PN junction diode. That is not going to change. So that's how it maintains the potential across the appliance. No time it is going to get the higher potential, so that there is a danger on this device. Okay, so this is how Zener breakdown works. Clear? Okay, so these are all the appliances which work on PN junction diode. You all have to remember it. Okay, next class we will be seeing the logic gates and numericals based on all these things. Clear? Thank you. Bye-bye.